Good morning, dear students. Welcome to another session of microwave and antenna. So in previous session, we discussed pertaining to concepts pertaining to loop antenna, in which we discussed regarding small loop and large loop. And then we discussed what is the radiation resistance and directivity of the large loops and the small loop. So now in this session, we'll go ahead with the discussion, which is pertaining to the concepts of horn antenna. So horn antenna was discovered by Sir Jagdish Chandra Bose, and the purpose of the horn antenna is transmission of the radio waves. So when we specify the horn antenna, we observe something as something which is in the shape of a horn, and which actually looks forward for radiating the microwave towards the other end, which helps in either radiating or reception of the microwave. Now, what is this associated with? So if I just have a look at this diagram, we can see that from this part, we can observe that there is a waveguide. So the waveguide is a hollow kind of structure which is presented in this way. So here we can see that there will be a gap over here, which will be surrounded by a material which helps us to transmit the microwave from one end to the other end. And this part, what we have is nothing but it is the horn. It is the horn. Because of this shape, we classify this as a horn antenna. And this horn is basically responsible for radiating the wave from one end to the other end. And what is the purpose of this waveguide? The purpose of this waveguide is to feed this horn section of the horn antenna. So this is with respect to horn antenna. So therefore we have two aspects. One is the radiating element, which is actually in the shape of the horn, and another one is the feeding point, which is basically the waveguide. Now we have one concept which is associated with the antennas. So when we consider the horns, we have different kinds of horn antennas. So in which the major classification is associated with two types. One is the sectoral horn and the other one is the circular or the conical horn. Now, again, here based on the flaring concept, we can classify the horn antennas. So what is basically meant by flaring? So if we just observe the structure in this case, we can observe that there is a tapering kind of structure in the horn antenna. So there is some tapering which we can observe. So the tapering is in say horizontal direction and even in the vertical direction, what we can observe. So this kind of orientation gives rise to what is called as flaring. So this flaring is basically done to improve the radiation efficiency and directivity of the beam which is being generated by the horn antenna, what we are observing over here. So now here what is done is this waveguide, what is there, its abrupt ending is extended. Its abrupt ending is extended, so that we have a extended aperture what we can observe over here, which is a mouth kind of structure for this antenna. So this basically say terminates the abrupt ending of the waveguide. So this overcomes the discontinuity what we have over here. So this entire thing can be classified as flaring. So this is the flaring concept what we have. So based on the direction of flaring, we can have the classifications. And apart from that, based on what is the shape of the waveguide and the antenna part, that is the horn part, we can have the classification. So these two classifications are based on the shape of the waveguide and the horns. So in the sectoral part, what happens is if I just observe the mouth area, so that is, this is the mouth area what we are considering. If I just observe the mouth area, we can see that in sectoral plane, it will be either square in shape or it will be rectangular in shape. So either I can have the mouth area which is square in shape, or it might be rectangular in shape. And in circular, what happens is the mouth area of the conical or the circular horn antenna will be circular in shape. So based on this, we can look forward for the classifications which are associated with sectoral and circular horn. So next part what we have is the sectoral horn. Under this, depending on the direction of flaring, we can have three classifications, which is sectoral H-plane horn, sectoral E-plane horn, and the pyramidal horn. So what is actually sectoral H-plane horn? Now, in the horn antenna, that is in this case, if the flaring is done such that if the direction of the magnetic field is maintained, if the direction of the magnetic field is maintained, we classify the horn antenna as sectoral H-plane. If the flaring is done in such a way that the direction of E-plane or the E field is maintained, we classify that horn antenna as sectoral E-plane. And another is the pyramidal horn antenna. In this case, what is done is the flaring is done in such a way, there is a direction of flaring is obtained in such a way that we maintain the direction of H and the E fields, that is magnetic and the electric fields respectively. So based on that, we have this classification. So when we observe it in diagrammatic form, this is what we have. So here, if we observe, we have the waveguide, we have the rectangular waveguide, we have this rectangular waveguide. So in this case, if I just observe in the H-plane sectoral horn, what happens is this side flaring is not introduced much. That is, you're not increasing the width of this part. Whereas in the upper part, if you just observe, what is happening is the length part over here, if I consider this as the length, this part is increased. That is, flaring is done in this form. If I just specify that this is length and this is breadth, if the length part is maintained greater than this breadth part, that is, if you just observe, this is the smaller side and this is the upper part is the bigger side. So if I maintain it in this form, then I obtain the horn antenna, that is a sectoral horn antenna, which will maintain the direction of the H-plane. So such kind of structure is called as sectoral H-plane. Similarly, we can obtain sectoral E-plane by having the flaring which is represented over here. So in this case, what is done is, if you just observe, we have the, say this is the breadth part of the waveguide and this is the length part. If in this case, if I provide a flaring which is in which this breadth section is extended to be larger as compared to the length section of the waveguide, then we obtain a sectoral horn which will maintain the electric field or the E-plane. So which is termed as sectoral E-plane horn or E-plane sectoral horn. And what happens in pyramidal horn antenna is the flaring is done in such a way that the length and breadth are enhanced, and the flaring direction is obtained in such a way in which we maintain the direction of the electric field and the magnetic field. So if this is the case, we obtain the pyramidal horn antenna. Now this is in association with the sectoral antennas, sectoral horn antennas. Now coming down to the circular horn antenna or the conical horn. So in this case, what happens is we have a waveguide which actually feeds the horn part, and we have this horn section which is helps in radiating. So here we observe that this radiating part, that is the horn part, is conical in shape. So when I consider a cone, so the horn part is conical in shape. Or if I just observe it from top, it will be circular. Its mouth will be circular over here. And if I make another observation is, if this is conical in shape, the waveguide which is used to feed has to be circular waveguide. So this is called as a conical horn antenna or circular horn antenna. Then apart from this, we can have two more classification, that is biconical horn antenna. So in this case, what we have a feeding part, which is the circular waveguide. And at the end, we have two conical radiating elements, which are actually the horns. These are the horns. So such kind of structure, what we have is classified as biconical horn antenna. Now let us have a look at the design equations which are pertaining to pyramidal horn antenna. So in this case, we have the feeding section, which is the rectangular waveguide, and then we have the flaring part, which is presented over here. So now in this geometric consideration, we can observe that this is the axis of the antenna element. Along this antenna, if I measure the length, this length will be termed as the axial length, which is denoted by the parameter L. Now what I do is, if I take the center point and then I traverse in this path, then I'll see that from this point to this point, I have the axial length along this direction. Similarly, at the other end, if I traverse and move down, here I'll see that from this end to this end, I'll be having a length which is given by L, which is the axial length. Now here, when we observe, we have some excess length, which is actually referred to as the path difference. So the path difference is identified by delta over here. So this is the path difference. Now, apart from this, we can observe that we have the mouth area, which is actually gives you the information pertaining to the aperture. That is, it is the aperture of the horn antenna, what we are considering. Now, if we try to represent these three sides in the rectangular form, so this length, what we are observing is, say, a very small, infinitely small. So what we do is we consider this triangle OB, say I'll write it as A. So when we consider this, can we represent these parameters L? Can we have some relation associated with these all parameters? That is what we will be observing. Next is one point to note down is theta, which is the flare angle. So depending on this theta value, we'll be classifying the horn antenna either as a E plane sectoral horn or H plane sectoral horn or a pyramidal antenna. So here we have, so based on this representation, so if I consider OBA, this triangle, what we have is, we have this end, which is whose value is given by, it is nearly equal to L plus delta L, and OB, its value is nearly equal to L, and this side BA is equal to A by 2. So if I represent this and consider this parameter, this is the representation, geometric representation of the consideration what we have observed. So based on this, we can see, if we apply the Pythagoras theorem, what we have, the hypotenuse square is equal to OB square plus AB square. So that is what is applied over here. And when we substitute the values, it is L plus delta the whole square plus L square plus A by 2 the whole square. So when we simplify, this is the equation what we are obtaining. And when we look at the structure, right, what happens is this delta value is very small. It is very small if you compare it with the length. So therefore, what happens is, if delta is very small, it implies that delta square is also very small. For example, if I consider delta is equal to say 0.1, So if I estimate delta square, it will be equal to 0.01, which is very small. So therefore, what we do is, based on this consideration, we equate delta square to 0 in this case. And on the RHS and LHS of the equation, we cancel off L square and L square. So we are left off with 2L delta, which is equal to A square by 4. So based on this, we can obtain the relation associated with the axial length delta and A, which is given over here, which is A is equal to, axial length is equal to A square divided by 8 delta, where A is the aperture of the antenna and delta is the path difference of the antenna. Now, since we have two parameters associated, one with the E plane and one with the H plane, we have two axial lengths associated with them. Actually, both the axial lengths will be same. Both the axial length will be same. So if I just observe whether it is in A plane or H plane, this length will remain same. But only thing is the path difference and the apertures in each of the planes might be varying. So here, when we consider that for E plane, we have A is equal to aperture square, which is associated with the E plane, divided by 8 times delta, which is associated with the E plane. So here A is the aperture in the E plane and delta is the path difference in the E plane. The same value I can obtain if I know AH and delta H, that is aperture in the H plane and path difference in the H plane, wherein I'll be obtaining axial length equal to AH square divided by 8 times delta H. Now, based on the triangle, what we observe, we can have the flare angle theta related with axial length delta or axial length and the aperture. So let us consider this. So if I take this angle, which is equal to theta by 2, that is based on this triangle what we are observing. So if I consider this angle, it is actually equal to theta by 2. So when I consider this flare angle, what I observe is, if I take the cos of theta by 2, I have hypotenuse upon the, adjacent upon the hypotenuse. I have adjacent upon the hypotenuse when I take cos of theta by 2. So which is given by L plus delta. So we have cos of theta by 2, which is given by L plus delta. So therefore theta is given by 2 times cos inverse L divided by L plus delta. So here we can observe that the flare angle can be represented in terms of the axial length and the path difference. Similarly, I can obtain the relation in terms of the axial length and the aperture by using tan of theta by 2. So when I simplify this, this is the equation what I'll be obtaining. That is theta is equal to 2 times tan inverse of A by L. So this is a relation in terms of the aperture of the antenna and the axial length of the antenna. So when we consider the next point, which is the directivity. So directivity, as we had seen in the previous sessions, right, what the relation between directivity and effective aperture. It is given by 4 pi by lambda square into AE, where AE is the effective aperture of the antenna. Next, we can relate the effective aperture and the physical aperture of the antenna with the efficiency factor. So here we can see that the efficiency is given by AE divided by AP, where AE is the effective aperture of the horn antenna and AP is the physical aperture of the horn antenna. It is the physical aperture of the horn antenna. So sometimes instead of gamma, they might use it equal to eta, and sometimes they use the term equal to K. So now for a horn antenna, generally it is observed that the efficiency is around 0.6. It is around 0.6. So therefore what we have, we can represent effective aperture in terms of physical aperture by using this equation, wherein we have AE is equal to 0.6 times AP. So therefore what we have is, when we substitute effective aperture in the above equation of directivity, that is this equation, see, we obtain a directivity which is equal to 0.45, for 4 pi divided by lambda square into 0.6 times AP. So this is directivity in terms of the physical aperture. This is directivity in terms of effective aperture. So when I simplify this, I can obtain the equation as nearly equal to 7.5 times physical aperture divided by lambda square. So next factor, what we have to look out is, we have to look out for the gain parameter. We have to look out for gain parameter. So here we can observe that gain is given by eta into D, where eta is nothing but the efficiency what we had seen. So which is given by AE divided by AP, and for horn antenna this value was around 0.6. So here, and previously we obtained what is directivity in terms of effective aperture, in terms of physical aperture. So now what we do is we can substitute D value in this equation and obtain what is the power gain, or sometimes it is referred as gain. So what is the gain for the antenna, horn antenna, which is under consideration? So this is the equation what we can obtain when we substitute for D and the efficiency factor. So in this case, gain is in terms of physical aperture is given by 4.5 into AP divided by lambda square. Now, if I know the aperture in if E plane and H plane, then I'll be able to obtain what is the physical aperture of the antenna, horn antenna. So which is given by product of the aperture of the antenna in the E plane with aperture of the antenna in the H plane. So this is the parameter what we will obtain. Now last aspect what we have to look forward is the half power beam widths. Half power beam widths, one in the E plane and one in the H plane. So which is given by this equation, which is 56 degrees into lambda divided by AE. And this AE is the aperture in the E plane. And the half power beam width in the H plane is given by 67 degrees into lambda divided by AH, where AH is the aperture of the horn antenna in the H plane. Now let us look at a problem associated with these aspects of horn antenna. Now here we can see we need to find the length L. So L is, this is nothing but the axial length. H plane aperture and flare angles theta E and theta H of the pyramidal horn antenna, for which E plane aperture is 10 lambda. E plane aperture is 10 lambda. Horn is fed by a rectangular horn with TE10 mode. Assume delta is equal to 0.2 times lambda in E plane and 0.375 lambda in H plane. Also find E plane, H plane beam width and directivity and the power gain. So with respect to this, we can observe what are the parameters they have provided. So here we can see that the parameter which is provided is for the pyramidal horn antenna, E plane aperture is 10 times lambda. So this is nothing but E plane aperture, which is AE. Now it is fed with the rectangular horn antenna in TE10 mode, and this parameter is nothing but delta E, since it is the delta in the E plane, and this parameter is delta H, since it is given in the H plane. It is associated with the H plane. So now what we have to identify is, we need to identify what is the axial length, what is the aperture in the H plane, what is the flare angle in E and H plane, what are the half power beam widths with respect to E plane and H plane, and what is the directivity of the antenna, and what is the gain of the antenna. So this is what we have to look forward. So now based on this, what is the axial length? So previously we observed that the general equation for the axial length for the pyramidal horn antenna is given by L is equal to A square divided by 8 times delta, where A is the aperture of the antenna which you're considering and delta is the path difference of the antenna. In this case, it is the horn antenna what we are considering. Now already we know that we can, if we know say aperture EE, AE, and delta E. So if I know these parameters, I can use this over here and obtain what is the axial length. So if I observe this, AE is given as 10 times lambda and delta is given as 0.2 times lambda. So therefore, when I substitute this over this in this equation, that is these two parameters in this equation, that is in order to identify the axial length, I substitute A as AE and delta as delta E. So what I'll obtain is I'll obtain the axial length in terms of wavelength, which is given as 62.5 times lambda. So this is the axial length. So now we have obtained one parameter, that is axial length. Next, we need to identify what is the aperture in the H plane. So in order to obtain that, we can make use of the same equation. Since the axial length has to be same, whether it is in H plane or E plane, therefore what I can do is I can substitute AH in this instead of A and delta H instead of delta. So when I consider the H plane, what is the change we will be looking forward? We will be replacing those two terms. So L will be equal to AH square divided by 8 into delta H. So when we solve this equation for AH, we obtain the aperture in the H plane as 13.693 times lambda. So next we need to estimate the flare angles. One is associated with the A plane and the other one associated with the H plane. So we can make use of the triangular representation what we had. So here we had theta by 2, this side it was L plus delta, and this side it was L, and this side it was A by 2. So we know what is AE, we know what is AH, we know what is the axial length, we know what is delta E. So you can use these things and obtain what is theta. So in this case, we are making use of, say, theta is equal to 2 times tan inverse of AE divided by 2L. So when we substitute the respective values of AE and the axial length, we obtain theta E, that is a flare angle associated in the E plane as 9.1480 degrees. Similarly, when we obtain for theta H, that is a flare angle in the H plane. So in this case, we need to use the aperture, which is associated with the H plane, which is given by 2 tan inverse of AH divided by 2L. So when we solve the equation for theta H, we obtain it equal to 12.5 degrees. So these are the two flare angles what we obtain in the E plane and H plane respectively. Now next we need to identify what is the half power beam widths for both of the cases, that is one for E plane and one for H plane. So for E plane we have 56 degrees into lambda divided by AE. So when we consider that, it is 56 degrees into lambda divided by 10 lambda. So in this lambda gets cancelled, and when we simplify it, we obtain half power beam width for E plane as 5.6 degrees. And lastly, half power beam width for H plane. In the H plane, we obtain it from this equation, that is 67 degrees into lambda divided by AH. So which is given by, when we solve it for the parameter, we obtain it around 4.89 degrees. Now lastly, we need to obtain the directivity. So either we can refer to the equation what we have simplified, or else we can refer to the main equation, that is directivity is equal to 4 pi by lambda square into effective aperture. And we know that we have the efficiency factor AE divided by AP, which is actually equal to 0.6. It is equal to 0.6. So therefore we can substitute AE equal to 0.6 times the physical aperture. Now, what is physical aperture? Physical aperture is given by the product of AE and AH. So if I obtain AP from AE and AH, I can substitute it in these equations and obtain the representations for AE and AP. So once we obtain this, we can substitute it in this equation and try to solve for directivity, or else we can use the simplified version of the directivity. So once we solve this, what we obtain is we obtain directivity equal to 1026.975. So which is a very good directivity. Now next is the power gain or the gain parameter of the antenna which is under consideration. So here gain is given by what? Gain is given by the efficiency factor into directivity. And for horn antenna, we had seen that the gain is efficiency is around 0.6. So 0.6 times D. So D value is already known, which is 1026.975. So when we solve for the gain parameter, we obtain gain equal to 616.185. So this is in association with the horn antenna. So this is all for today. Let us meet in the next session. Thank you.